So hello everyone. Thank you first for staying around for my talk for as late as it is now. Thanks to the organizer for giving me the opportunity to give this talk about the work I've been doing in collaboration with Konstantinos Kordis and Tom Schlossnik in Prague. I should preface my talk by saying it's a work in progress, but hopefully you'll still find it interesting. So let's jump into it and start with the motivation for this work. So you might already know all of this, but I'm going to say it anyway. So dark matter, it's a long history of successes in explaining astrophysical observation, from the dynamics inside of clusters to galaxy rotation curves, peculiar objects like the bullet clusters, plus also its successes in explaining a variety of cosmological probe, leading to lambda CDM being currently the standard model of cosmology, with cold dark matter being dominating the universe matter content. However, on the other hand, there is still no signal from direct detection experiment, or I should say no unquestionable signal, since we still have the detection from the annual modulation detected by DAMA, but which is still hotly debated. Also nothing from the LHC so far, fortunately, and also a bit of trouble in cosmology too, especially when you compare simulation to observation at small scales, especially concerning the density profile of galaxy, the missing satellites problem, and so on. So all of this provided some motivation for searching alternative to dark matter, and one of such alternatives, perhaps the most well-known, the most famous, is the so-called modified Newtonian dynamics by Milgrom in 1983. And one way to formulate those modified Newtonian dynamics is by a modification to the Poisson equation with the inclusion of a free function mu. I say free, but it's not entirely free. It has limiting forms in order to recover Newtonian behavior at small scales and fit the rotation curves at larger scale. But the detail and the actual choice of the function is often somewhat arbitrary and lack theoretical motivation. And also another problem is the fact that it's not fully it's not a fully relativistic theory, and so the realm of validity of this equation is hard to know. As a consequence, a number of relativistic theory that recover MOND-like behavior have been proposed in the last 15 years. The original being the so-called t-TeVes for tensor vector scalar. The t-TeVes theory of Bekenstein from 2004, and which has been then generalized by Konstantinos Kordis in 2008. Then other theories such as the generalized Einstein ether theories, biometric theories, and so on. But all of these theories here possess a similar ambiguity as MOND, in the sense that there's also a free kind of arbitrary function in the Lagrangian. Also, another thing is that those new theories introduce new degrees of freedom into the physics of these models, and as a consequence, it often blurs the line between what can be considered as an effective additional dark force or something that could actually be achieved by a certain type of dark matter with exotic dynamics or exotic couplings. I'll focus today on another model that recovers MOND-like behavior, which was recently proposed by Babichev, Defayet, and Esposito Farese in 2011. This model uses t-TeVes as a basis and adds a Galilean term, which leads to the Galilean term leads to a convenient Vainshtein screening mechanism of the effect of the scalar field in environments such as the solar system, which is pretty convenient. It has the nice property of removing the free function, so no longer this ambiguity is gone. And as I said, it recovers MOND-like phenomenology. In the rest of my talk, and me and my collaborator choose to dub this model the g-TeVes model for the Galilean extension of the t-TeVes theory. So the theory, the action for this theory looks like this. One thing to notice first is that there's two metrics. There's j-tilde mu nu and j mu nu, and two metric with this formal relation between them: the Einstein metric j-tilde and the matter, the physical metric j, which is coupled to the matter fields, which couples to the matter field. So let's have a closer look at the term in this metric. So you have your regular Einstein-Hilbert term. One might want to add a cosmological term with respect to the physical metric here. Then you have the Einstein ether action, still pretty regular stuff. And then the last term, which contains most of the changes. So in the original TeVes that I reproduced here, you have the following form with, again, a free function f. And here in this g-TeVes model, you have the first term, that's the canonical kinetic term, which is proportional to this constant epsilon c. Then you have a second term which is proportional to the inverse of a tilde naught. This term provides an analog to the mu function in MOND, in the sense that it is the thing that gives the limit, which is responsible for dark matter-like effects in astrophysical systems. The third term, which is proportional to k-gal, is an example of the so-called Paul Galileon-Lagrangian of the Fab4 scalar field models, and it has the effect of suppresses the additional force from the scalar field in high curvature region. And finally, one last term, a mass term for the scalar field. Yeah. So now that I presented you the model, what about the constraint on the three parameters of the models? So the original author of this model have derived some constraint from what I would call small scale, so galactic and subgalactic scale. On such scale, the non-relativistic acceleration takes this form with the traditional Newtonian grad phi and an additional the spatial gradient of the scalar field phi, which provide an extra force, and it's this extra force that is tuned to give which is constrained by rotational curve measurement, for example. So a quick look through those astrophysical constraints. So the A0 that appears here is the same A0 as in MOND, so it's therefore constrained by rotational curves measurement. This k-gal term needs to be big enough to dominate in solar systems, so to provide this nice screening mechanism, but it needs to be small enough so as to not dominate in low baryonic systems that still show mass discrepancy in the observation. Again, epsilon c also needs to be small enough so that the kinetic term do not dominate too much. And so that's for the three main parameter of this model and the astrophysical constraint. But please keep in mind that the actual number that constrain this parameter have been obtained in a kind of back of the envelope calculation, so they need to be taken with caution. So this is nice and all, but what we want to do eventually is to test this theory and to see how it fares in a cosmological context. So the first steps towards this and towards deriving the cosmology of the g-TeVes model has been performed by the colleagues of mine recently who derived the background evolution of this g-TeVes model. They derived the field equation assuming FLRW symmetry. And in FLRW, the action can be reduced to this more simple form here. Then, without going too much into detail, after adding the matter content to this, one can arrive to the equivalent of the Friedmann equation, as well as a set of coupled equation that gives you the evolution of the field amongst the scalar field phi, amongst other things. So once you have your equation you can write your code that will be able to compute the evolution, the background evolution in this model. And then one might want to see if some sets of parameters of the g-TeVes model are able to mimic lambda CDM expansion. And the method to do this that my colleagues choose was to try to minimize this quantity, which is pretty much the integral of the relative difference between a reference lambda CDM h of z and the h of z that comes out of your g-TeVes model. A few words of caution. When exploring the parameter space of g-TeVes, you realize that it's quite tricky because there's many sets of parameters that lead to failed universe, we could say, that never reaches a scale factor of 1. For example, some models, so here it's the evolution of phi dot. You see that some models stop at some point. They have a thwarted evolution when actually phi dot, so the time derivative of phi, tries to cross 0. For example, that's one example of failure. Another failure is like damped oscillation in the scale factor A that actually lead to a static universe in the end. So those are the kind of model that you need to get rid of and be careful. So here are the results of the minimization of the quantity I showed before. There's 4 cases considered, whether or not you include the astrophysical constraint I mentioned, and whether or not you allow for the inclusion of a CDM, you allow back CDM into the model or not. In this plot here, you have the best fit for all the 4 cases, and what is shown is the ratio of the h of A from TeVes divided by the the reference h from lambda CDM. It's decently close, especially you might want to concentrate on A and C because they really do not have any CDM component. You see that they fare much better than GR with no dark matter, but still quite a bit of difference. But it's not completely crazy values. Of course, as it was kind of expected that as soon as you put back CDM into it, you get a much better fit to h of z. And here are the best fit parameters. So a few statements from this. So the g-TeVes model gives a reasonable fit to lambda CDM, especially given the actual large range of redshift that we do the fit on. Also, there's a kind of an arbitrary weighting that is done here. It gives equal weight to logarithmic interval of A, so that must also influence the fit. You might give different results if you give more weight to lower redshift, for example. And another thing related to this is that it has yet to be confronted to actual data. This is important because the data that we have on h of z is not actual measurement of h of z. It's always integral of h of z. So there might be compensation effects, like for example this bump here might be compensated by this bump here, which might allow for an actual good fit of the data from standard candle. So I have no time to get into the details of why it works, but like I can give a few CDM-like effect. Like for example, in the radiation-dominated era, the kinetic term of the scalar field behave as a dust component, which helps a lot. And in the matter-dominated era, these first effects disappear, and then it's the increase of phi that kind of that results in an increase of the effective Newtonian constant, which in turn makes matter heavier and helps recover lambda CDM behavior. Compared to the original TeVes model with the original Bekenstein free function, the fit is slightly better, and again it's thanks to this effect during the radiation-dominated era, which are not present in the original TeVes. Again, without going too much into detail, we can think of additional term to add in the Lagrangian, but this still seems tricky to add them at this moment consistently in the action. So I won't go too much into detail. So this is nice, and it's an encouraging first step, but so far in my talk, you've noticed that I've conveniently ignored a major hint of the existence of dark matter. This guy here on the screen, the cosmic microwave background. And the CMB has always been a major hurdle to clear for any consistent theory of gravity. And this is especially true for model without CDM. And the standard model lambda CDM gives an excellent and impressive fit of the Planck CMB data, the Planck power spectrum, with as little as 6 parameters and a few assumptions that people tend to forget to speak about, but anyway, 6 parameters. And this is important because the CMB power spectrum indeed probes and kind of proves the presence of cold dark matter through the fitting of especially its first peak. Indeed, these so-called acoustic peaks of the CMB originates during the oscillation, originates from the oscillation in the baryon photons fluid during radiation-dominated era, and it's intuitively obvious that those oscillations will be different whether or not you have an additional massive non-interactive component around, such as cold dark matter. So briefly speaking, CDM lowers the first 2 peaks compared to the third. So the relative height of this third peak is kind of a killer for this kind of models. And indeed, this is the kind of observation, the third peak, that has put serious strain on TeVes, on classical TeVes model, as it is very hard to reproduce. Of course, the third peak is not the only thing to fit, right? You still have to fit all the other peaks at the right height and the right position. So, and a quick note, this is so the blue line is the TeVes model. It's a crude plot here. It's not like the best fit TeVes model ever, but it's just representative of the kind of things we get with TeVes. So in order to confront this extension, this g-TeVes model, the extension of TeVes to CMB data, we thus need to go further than just the background equation, and we need to derive the perturbation equation. I won't go into detail because that's messy, and because there's only 1 hour left in the whole conference, and last but not least, because I don't think I'm quite qualified to really talk to you about this, and I give lots of props to my colleague Tom Sloshnik for dealing with this mess and deriving those equations. Once you have the equation, me and my colleague Tom Sloshnik, we implemented it in the public Boltzmann code class from the vanilla version of the code. So far, the code seems stable, but regardless, we're still currently testing it against an independent code by Konstantinos Kordis, a TeVes code by Konstantinos Kordis. As is often the case in this type of model, the exploration of the parameter space is quite complicated, as I already mentioned. There is some local minimas, forbidden region of the parameter space, etc. So it's a bit hard to do fits in this kind of situation. So I used a combination of robust minimizing technique and also Monte Carlo Markov chain techniques that are kind of more adapted than the classical metropolis Asting algorithm, for example. So here you have plotted here in green the best fits from the g-TeVes model compared to the Planck data, which are the little crosses. Didn't put the error bars because otherwise the plot would be unreadable, but you kind of guess with the dispersion of the point. So visually it's pretty good. As you can see, it fits pretty nicely, those peaks, especially the third one. Of course, in terms of chi-square, we're pretty far compared to lambda CDM. We have around 2,500 multiples, and we have a chi-square of 3,100. So technically, it's excluded compared to what lambda CDM can give. However, compared to the general TeVes, it's quite encouraging. It manages to raise up the third peak without screwing up too much the rest of the spectrum. And actually, if we do the fits only on the first 3 peak, we can pretty much get a chi-square that is as good as lambda CDM, which is pretty cool. However, I just again want to repeat that it's still a work in progress. We're still in the exploring phase, so I probably won't be able to tell you right now exactly why it works so well, but it's something that we're actively working on. One thing that I can mention is that it seems that the best fit model tend to require the k-gal term to be close to 0, which is kind of bound to lead to some trouble in solar system tests. But still, it's quite interesting. And not only is it interesting, but it's certainly a much better level of agreement than what GR with just lambda and baryons would give you. Like, we did some tests, and the best you can do is like chi-squared that is 10 times as high as this. Going back to TeVes quickly, when people try to fit the general TeVes to CMB data, they found that introducing neutrinos can help. So that's also something that we explored. We introduced neutrinos in the g-TeVes model and did the same kind of minimization and fit of the Planck data. And we obtained this best fit. It's kind of hard to see. You can maybe see some differences here around the peak. And there's a noticeable improvement. For just one parameter, one new parameter and one new component, there's quite a non-negligible improvement in the chi-square. So neutrinos help, and exploration seems to prefer values of the mass of the neutrino that is significantly non-zero. But again, the chi-square is still not on the lambda CDM level. Also, in this kind of model, when you go back to the behavior of the background evolution to h of z, again, it's not a really good fit of lambda CDM, but it's not worse than what I showed before with, like, during the dedicated background exploration. Nevertheless, the improvement between the two is quite interesting because several things are left for us to explore in this analysis and to consider. For example, we have yet to implement tensor mode. Maybe not much effect because it will be probably around at large scale, but you never know. We need to have a closer look at the initial condition in this model, and in particular the inclusion of isocurvature modes. This is very, very important given the fact that the fits here tends to prefer quite high value of the scalar index ns, and it was the same in the general TeVes model, and it helped. It actually helped a lot to consider those modes in TeVes. So we'll do the same. And we might also even consider some extra ingredients in the model, maybe not in the action itself, but maybe in the form of an additional component, like, for example, sterile neutrino, which might give interesting results too.
How big should be this NS?
NS, for here, I think it's like 1.2 or something like this, yeah. So it's really high. So, yeah, it's blue. It's very blue, extra blue, ultraviolet. Okay, so I reached the end of my talk. I thank you for your attention. As I said, we're still in the trying to understand what's going on stage, verify the code, etc., add new stuff. But the first results are quite encouraging, and we have a lot of stuff to try. I guess the only thing left to say is stay tuned for the next development. And hopefully, in the end, it will allow us to answer the question, is there still any room left for this TeVes-based theory to survive in the light of current cosmological data? And thanks a lot.
Questions?
Do you have caustic problem in g-TeVes also? Because TeVes has caustic problem. So do you still have caustic problem, or you managed to cure in g-TeVes caustic problem?
As far as I know, we managed to get rid of this problem, but I would say that my two colleagues are probably more qualified to answer this question. So, so far we haven't encountered any. So I want to say no to your question, but I wouldn't be able to get into details. Sure, we can definitely talk about this.
First of all, a historical, is this working? Historical remark. You mentioned TeVes as the first covariant MOND theory, but actually the first covariant theory is by Bob Sanders from the 90s. It was a scalar field. and then it was a scalar with the vector. There's a whole development that at the end reached TeVes in 2004, but there are more theories before that. But anyway, that's just a comment.
But thanks for the historical.
The question is, can you do you get an A0 value from the fitting from the CMB fits?
So we have values, but I think it's. I could give it to you. I have it somewhere on my computer, but I would say it's still too early to take it seriously.
But it's more or less compatible with the value we measure from galaxies, or?
Yeah, it's in the nice ballpark, but it might be. I would say it's like not more than a factor of 10 bigger, and not less than a factor of 0.1 bigger. Like in terms of log, it's plus or minus 1. But yeah.
You mentioned that there was trouble in comparing the expected, say, luminosity distances with standard candles. Would you be able to then just compare, say, an H of Z with cosmic chronometers or radial BAO?
That's definitely something. It's true that we kind of focused our attention on the CMB first, because it kind of also includes already a test of. It includes a standard ruler inside of it, like with the location of the peak. But if the CMB does not kill those models, we will then go to the next stage and add as many probes as we can, including the BAOs, supernovas, and so on.
No more questions?
Here.
I see. What is the thing that's actually giving the potentials into which the baryons fall? So the scale is oscillating because there's a mass or something like that, or what's the?
I would assume something like this, yeah. But again, there's different in this kind of model. There's different regime where at the beginning it's more like in one of the regime it's going to be the scalar field that dominates. Then it's going to be like the ether side of the theory that dominates. And as I said, so far I'm still unable to give you a straight answer, and I wouldn't risk myself to give you an answer to this. Like in the next few weeks, we will sort it out. So you can just knock on my door and my office, and I'll tell you.
Okay, thanks a lot.
Thank you.